Hello everyone and welcome to Module 1 of this Quantum Computing Beginners course. The goal of this module is to give you a very informal, a bit historical introduction to the theory of quantum mechanics, but mostly to get you excited about what you learn in the modules to come. So in this module we will discuss some of the most counterintuitive features of quantum mechanics without appealing to any mathematics just yet. So I will show you a very famous experiment called the double slit experiment, which hopefully at the very least will leave you very intrigued. And this will be the starting point for us to informally discuss the rules or the axioms of quantum mechanics. And just as a heads up, in the modules after this, we will review the mathematical tools that are necessary to formally understand the basics of quantum computing. So let's start with a brief recap of classical physics. So in general, physics aims to understand how nature works. All of the successful theories that have been developed before the 1920s are now grouped under an umbrella called classical physics. And classical physics has two main components: Newtonian or classical mechanics and electromagnetism. Now, classical mechanics deals with the movement of macroscopic objects, so large-scale objects, for example, planets or, say, tennis balls. And for simplicity, even though these objects may be large, they're often modeled as classical particles. So essentially point-like objects of negligible size that at any given moment occupy a very well-defined position. So you can pinpoint exactly where they are. On the other hand, electromagnetism deals with the interaction of classical particles that have an electric charge. And at the heart of electromagnetism is the concept of a wave. And we will talk about classical particles and wave in more detail very soon. And don't worry at all if you don't feel familiar with classical mechanics or electromagnetism, you don't need to be. So this discussion that we'll have in this module is mostly informal, and I am mentioning them mostly to give some historic context for quantum mechanics. And anything that you need to know or understand, I will tell you. Now, together, classical or Newtonian mechanics and electromagnetism explain most of the phenomena that we regularly observe. For example, the movement and collisions of billiard balls are well explained by classical mechanics. Heat and temperature are also well understood by studying the movement of particles using classical mechanics. On the other hand, one can understand many of the properties of light as an electromagnetic wave. And so, what is it that led to the development of quantum mechanics? Well, towards the end of the 19th century, some physical experiments produced observations that could not be explained by classical physics. So neither by classical mechanics nor by electromagnetism. And in particular, many of these experiments investigated matter at increasingly small scales. And through much of the 19th century, physicists had kind of reasonably assumed that the rules that govern physics at large scales were equally valid for small scales, so for microscopic systems. But in the early 20th century, the number of experiments that were not matching the classical predictions kept increasing, and it became clear that the behavior of very small systems, we're talking here about systems of the order of 10 to the minus 10 meters, could not be explained using just classical physics, and that a new theory was needed to make sense of all of these experiments. And this theory, as you can guess, is quantum mechanics. And in this module, we will describe one of these experiments, which highlights some of the novel features of quantum mechanics. And this experiment is commonly known as the double slit experiment. And so, just as a tip for approaching this journey into quantum mechanics, as you hear about it for the first time, some of you, it will probably sound very unnatural, and you'll probably be left wondering, how could nature possibly be this way? And this reaction is completely justified because your perception of nature is rooted in the macroscopic world, so in the world at large scales, which follows the rules of classical physics. So what I suggest that you do is to put yourself in the shoes of a physicist and say, okay, I have a set of observations from these experiments, and I have to come up with a theory to explain them. And once you adopt this approach, you'll probably become more comfortable with quantum mechanics. At the very least, you should realize that the experiments involved here are about particles that are 1,000,000 times smaller than the width of a hair. So when you think about it, there is no reason why you should have an intuitive understanding of the world at that scale. And in fact, the experiments that we will see should be the starting point to build that intuition. So without further ado, let's look at the double slit experiment, which is our starting point to build some intuition about quantum mechanics. So the double slit experiment is a landmark experiment in physics. It was first performed by Young in 1801 using photons, and then again by Davison and Germer in 1927, who performed the same experiment using electrons instead of photons, and they observed the same qualitative behavior. Now, to understand the behavior of quantum objects, it is often helpful to contrast this with the behavior of classical objects. And so for this reason, I will show you the double slit experiment 3 times, first with classical particles, which obey Newtonian mechanics, then with macroscopic waves, for example, water waves, and finally with quantum objects like electrons or photons. And so before we dive into it, let me summarize the main properties of the 2 classical objects that will be involved in the experiment. These are classical particles and macroscopic waves. So a classical particle is an object that obeys Newtonian mechanics. For simplicity, it is usually taken to be a point-like object, meaning it occupies just a single point in space. So it is an object of negligible size. And probably the most intuitive way of thinking about classical particles is thinking of them as tiny tennis balls. Now, a particle has a mass, which determines how heavy the particle is. Now, a particle, because it is point-like, it has a very well-defined position, so you can pinpoint exactly where it is. So it is at a precise point in space. And when we're thinking about motion, one can, for example, describe a particle by its position and also its velocity, which refers to the speed and the direction of motion. And given position, velocity, and mass, Newton's laws allow you to describe exactly how the particle will move subject to any forces. So now, what about waves? So a wave, on the other hand, is a phenomenon that is spread out in space. It usually arises from a disturbance of some sort in some medium. As an example, you can think about the water wave that is generated when you throw a stone in a pond. Now, properties of a wave include, for example, amplitude, which is how tall the peaks of the wave are, frequency, which is the rate of oscillation of the wave, and wavelength, which is the distance between 2 consecutive peaks of the wave. Now, a wave is usually caused by the individual motion of particles, but it is the collective motion of all the particles that gives rise to the effect that we generally associate with a wave. Now, you can understand this by looking at the animation here and focusing your eyes on a single particle. It helps if you choose a particle that is near a vertical line on the grid. And now if you focus your eyes on this particle, you'll see that the particle is only moving up and down vertically and is not moving horizontally at all. So it is really the collective motion of all the particles that gives rise to the impression of the wave moving to the left.